bonjour à tout le monde. Si je retiens quelques leçons, je vais attirer votre attention sur le fait qu'on va changer de langue. Vous êtes prêtes? So it's a real pleasure to introduce to you our next keynote speaker, Professor Lindsey Richland from the University of California, Irvine. Where she currently works as a professor of education and where she is the associate dean of the graduate program in the School of Education. So Lindsey has a background in anthropology, developmental and cognitive psychology. She is a leading researcher in the fields of cognitive development, learning sciences, mathematical thinking, and analogical reasoning. So inviting her to this conference was a natural and very obvious choice, and we're extremely happy that she accepted to make the long journey to be here and share her work with us. So at UC Irvine, she directs the Science of Learning Lab, a collaborative research group dedicated to the understanding of how children think and learn. Her empirical investigations stretch from the controlled conditions of the laboratory settings to the complexity of real-world classrooms, examining how reasoning and learning unfold in dynamic, everyday contexts. Her team works closely with teachers, families, and community members to understand learning as it happens, so in school settings, at home, and through social interactions. And one of the lab's core goals is to identify the best ways to support children in developing the kinds of thinking skills and as the ones that experts use, so particularly in math and science. So her work also stands out, so not only for the scientific depth, but also for its educational relevance. Indeed, she is committed to bridging the domains that are often treated separately, so recognizing the importance of connecting cognitive science research from laboratory settings to real-world classrooms. So another hint as to why these two conferences follow each other. And beyond her work, Lindsey has also contributed to shaping large-scale educational interventions. Her research has been published in some of the most prestigious journals in the field, including Psychological Science, Cognition, Developmental Psychology, Journal of Experimental Child Psychology, and many others. So please join me in welcoming Lindsey Richland to present her research with us.
Thank you for a very kind introduction, and I really appreciate the opportunity to be here. These are my favorite topics, so I'm so excited to be at a whole conference thinking about learning, analogy, math, all of the rest. So I had too much to talk about, and I just tried to throw a lot in here, so I apologize if it's too much, and we'll skip around if we need to. But I want to start and really be very precise about what I mean and what I'm looking at, and then you'll see once we get into the real world, things get kind of messy, right? And that's sort of the way it works, and that's the only way, I think, to do work that is actually going to be meaningful in the world. So you kind of have to go back and forth. So at least that's how I think about it. So I take a very formal definition of analogy coming from a structure mapping model. So really a very classic definition, the relationship between A and B and the relation between C and D are the same, right? So this is sort of a formalization of what we mean by analogy. But when you're in a learning context, this often looks much richer. So here we have two models of a volcano. One is a real-world picture, right? You can see the parts. The other one is a symbolic diagram where the rock cycle is highlighted. And the intention here of putting these next to each other is so that you are drawing a connection between the two, recognizing the relational commonalities within the real world as being those that are demonstrated in this symbolic representation, even though they don't really look the same. So here, it's not the very precise, clear one-to-one correspondence that you might be able to design in a laboratory setting, but you can see here these relational structures in these different contexts. Now, Piaget and Helder and Piaget argued that analogy is one of these really core pieces. It's one of expresses the general characteristic of formal thought. It was their argument. And this So specifically, they were talking here about this notion of second-degree operations. So this higher-order relationship here, right? This overarching. So I figured I would bring this back to Piaget because that's where really this work started. And I think, anyway, that lends it. I'll get back to it again. It lends a really interesting and important dimension to the field. In mathematics, it's a perfect place to be looking at analogy because it's all a system of relationships. And you see within mathematics, there are relationships between problems, between concepts, between solutions, between sort of broad representations. So to formalize this, an equivalence relation is really a relationship between, you know, the two sides of this equal sign, right? This is an equivalence relation. An expert might see these two as the same, right? Anyone who really understands an equivalence relationship is quite clear that these are going to be the same. But this is also an important point because this is something we know kids have a hard time with. Martha Alibali, who will be speaking tomorrow, has done a lot of work about this. There's a lot of evidence that children really recognize these structurally as distinct at first and then have to learn and understand these equivalence relations. So the fact that analogies are out there and the relational correspondences are out there, that's not enough, right? We also need to actually understand them, and children need to actually be able to represent those relationships and correspondences. So now Piaget raised these questions about, well, when can young children reason by analogy, right? So if they were arguing that this is really something that was part of formal operations that wasn't necessarily available to younger children, right? So the argument was that children can map relationships, but not those higher order relationships by 5 or 6. So if you're going back to this, they might be able to represent, you know, sort of the A is to B, right? But not these higher order pieces. By 8 to 10, they can map those higher order relations, but not be very resistant to challenge or distraction or difficulty. And that really, the field really kind of has pushed these questions. But then by 11 and a half, children should be able to reason analogically. So this was sort of the starting point from the field. And like many fields, Piaget's arguments really set the ground for hundreds of researchers to kind of jump into the fray and try to decide, is this right? Are there ways? Can we find this earlier? You know, what are the parameters under which children are able to reason? And I want to just put this in front of you to kind of get you thinking about what analogy looks like younger. This is a video clip from a data set that we collected on children's home language. And so, you know, see if you see analogy here. So if you can hear anything. Oh, I guess that's only my audio. Okay, but you have the transcript. There's a way to.
That tornado looks like a mean monster.
Okay, so I don't know if you could hear that too well, but anyway, there's the tornado. It looks like a mean monster. And in case you don't know the English word, a tornado is a big storm, right? So the idea here is that, you know, this child is not in the midst of a storm. It's first pretend. So she's first doing this one layer of creating this notion of a tornado. And then she says a tornado is like a mean monster. And a mean monster is also this sort of mean, powerful, scary thing, right? So here we're really seeing evidence, I think, you know, that children are doing analogy, right? And that actually has come out in the field. And there's been a lot of research showing that children are attending to relations and are able to map relations even within the first year of life. But there are constraints, right? And so we know there are constraints. But that being said, children seem to be kind of born and organized to do relational thinking. The Penn, Povinelli, and Holyoke work argues that young children's relational thought is really distinct from the way other animals do relational and analogical thinking. This example, I don't know if you can really see from here, it's a really nice, I think, comparison where You see chimps who are learning the heavy relation, so they have to take something heavy and put it in one box and take the light one and it goes in a different box. And it takes about 800 trials, but they can learn that. Then they get a new representation and it takes about 400 trials, right? The human child can do it in about one, right? So they do, they go the heavy and the light one's different, so they infer that it should go in the other box, right? So it's a really different sort of reasoning, it seems to be, that children are coming into the world maybe really organized to attend to relations and to be able to map those kind of correspondences. But they're not always great at it, right? They're not doing it like adults. So I've really been, throughout my career, interested in these two questions. One is, what makes a child able to do analogy? And then the second piece is, what makes them likely to do it? What is that kind of invokes and invites them to use their relational thinking in any particular moment? So I'll just say a little bit about the ability piece. This is where much of the research in the field is. So those of you in the field may be familiar with it, but really, there's been a lot of argument that there are a few key contributors. So one being knowledge. You have to have prior knowledge in order to be able to reason analogically. It's not really a surprise that if you don't have knowledge, you aren't able to think. If you don't know what a tornado is, you're not going to be able to make that analogy, right? The second piece has been argued to be executive function. So in order to take two relational structures, align the correspondences, map between them, make inferences about the target, this takes a high amount of working memory to sort of hold that active, inhibitory control to not, to figure out what to disattend to not attend to the perceptual features that may or may not be irrelevant, and to also disattend to features that when they map are ineffective. So we did a study using a big data set to try to understand how these pieces fit together, and can we explain the long-term growth in analogical reasoning, looking at these different capabilities. So in this data set, this was the National Institute of Child Health and Development in the United States, Early Child Care and Youth Development, it's the longest name. 1,300 children were followed from birth to, actually they're still being followed, but this analysis looked at up to 15 years. So here, 539 had all the pieces, the data that we were looking at. And basically we looked at analogy scale at 3rd grade and at 15 years. This was a formal analogy task, a verbal analogy, cat is to kitten as dog is to what, sort of in that A is to B format that I was describing. And because it was a good data set, we were able to control for a fair number of background variables. And we were looking at whether knowledge predicted these skills using a couple of different measures, and then a few measures of executive function. So short-term memory, it wasn't a whole working memory, but short-term memory, executive function, the Tower of Hanoi, and the executive function Stroop task, as well as an attention task, so the sustained attention task. Tower of Hanoi is one that has been looked at. It's a little bit more of a combination executive function measure, and that's something that I think is important when you're thinking about something broader like reasoning. But it's the Miyake analysis put it as inhibition and a little bit updating. And basically, what we found was that all of these pieces did predict growth in analogical reasoning, or they predicted an analogy scale over time when you looked at the average over time. So both knowledge, the short-term memory, and the executive function measures were all predictive. When you looked at gains in particular, so controlling for where they were at 3rd grade and looking at the age 15, you saw that the Tower of Hanoi was the most predictive. So basically this argues that these are some key contributors, tells us that these are skills that develop over time, and higher order thinking may be particularly tied to executive function because it's sort of setting up this reasoning system, which maybe allows you to take in more information. So I've gotten interested in thinking about, okay, if we know something about what that developmental trajectory looks like in terms of ability, we know that not everybody is using their executive function, their reasoning skills all the time. What gets them to use that reasoning? Where does that show up? How do things like the pragmatics of a context, a moment, the goals, what's happened right before the learning, how does that change what happens and the likelihood that children are doing their reasoning? How does their prior experience and their socialization change that? Because we have this sort of intuition that, well, children's upbringings, is going to change the way, whether or not they're likely to try to reason through a situation or try to memorize something. So we were trying to get data. What does that actually look like? We also care because developing the ability and the likelihood of using analogy in a context is very much like what experts do, right? So experts, think about Chase and Simon, Mickey Chi's work, are really about paying more attention to relations than surface features, right? So experts will notice the relations, the sort of key underpinnings of representations rather than paying attention to the surface, whereas somebody who doesn't really know what they're looking at, doesn't have a lot of background knowledge, might very well try to just pay attention to the surface features and really be keyed into that. Brunner talked about going beyond the information given. I'm sort of going to the big theorists here, starting with the Piagetian framing. But really these experts are asking why things work. How do they work? They're challenging the rational underpinnings of arguments, right? They're really trying to go straight for these key relational pieces. So we want kids to do that, right? That's our goal. I mean, when we're teaching, I think about STEM, science, technology, engineering, mathematics. In particular, when you're teaching children in these fields, you don't want them to just memorize these are the steps of the rock cycle. You want them to understand the system, and you want them to ask questions about how it all fits together, how it works. We want kids to be looking for relations. So how do we get them to do that? And so you can think about this as a relational mindset, right? So this is this, this tendency to preferentially notice and reason on the basis of relations rather than focusing on object features. And this is sort of like a propensity to use relational attention. So that may be something that is particular to a content. So if you have a chess expert, you might do it in chess but not do it elsewhere. Or it may be something that's kind of the stable characteristic of, you're the kind of person who just likes to understand why things work. Whatever it is, I don't like to just memorize things. I want to know how and why, right? Some of you academics may, resonate to that. It also may be temporary or may be stable. So the original notion of the relational mindset came from Vendetti and Holyoake, who showed that you could prime a relational mindset by getting adults to do really high effort relational thinking. That makes them more likely to look relational on a new task. So it can be these kind of temporary things. So I want to think more about kind of what guides these tendencies and how this might change over time. Okay, so let's bring it back to math. I want you to think about what you notice here, okay? So this is about a problem. This is a teacher who is talking after having given this class a problem. Ken and Yoko are shooting baskets. Who's better? You can see the table right there. All right, so what do you see? Just kind of think for a minute. You can look at this. If you were in my session this morning, I made you look at a classroom. Here we're actually looking at a math lesson. All right, so there are a lot of things to look at here, but the key here, so the instructional goal here, was an analogy between one solution strategy and another, and the goal was to show that they were the same, right? So this, the aim here was teaching multiple solution strategies to a particular problem, and then helping scaffold the kids from a pretty simple type of explanation that works, but it's slow, versus actually, sorry, I'm wrong. This was one that's incorrect, and the other one is the solution that is correct. If I'd have moved it to there, that's another one that's correct, and they're both correct, right? The LCM, the division. Okay, so anyway, multiple solution strategies. The goal here is to get the kids to be comparing across these solutions, to understand the broader conceptual schema by comparing these representations. But it's very possible that kids were looking at all kinds of other things here, right? You probably were looking at things, you know, why is she doing this? What is she pointing to? Is there something about, you know, the names of the strategies that are confusing? How about Yoko? Do you know somebody named Yoko? I don't know. You know, so there are lots of things that could be paid attention to. And so I think in order to do the relational thinking, we need those prerequisites that I was talking about. You need prior knowledge, you need adequate executive function, but we also then want to think about the pragmatics of the context, what has been set up so that the child actually feels like they need to learn and they need to be attending to relations. And then the last piece is socialization. And I want to talk about that some more. So how do we get kids to think that that's what you do in math, is that you look for the relations. You're trying to figure out how these pieces fit together. And I'm going to argue that relational attention is distinct from relational reasoning ability, and it may play a key role then in modeling relational analogical reasoning and how it unfolds in learning context. So when we're thinking about socialization, you know, so I said we have some pretty good sense about how they develop relational skills, but how about the socialization? So I want to start by looking at language inputs, because we know that that's a really powerful mode of communication, socialization, and shaping children's cognitive development. And so for this one, we took a sample. I kind of joined this project late, but this was a sample of 64 children that were sampled to reflect the diversity of Chicago, which is a pretty diverse U.S. city, though there was the constraint that these had to be English language primary families. And these kids were followed we're still following them, but they were visited 12 times from 18 months to 5 years, videotaped for 90 minutes per visit. So this led to a lot of data. So this was a way to capture kind of what the home language context looked like for these children. And they were not given any instruction. Parents were not given any instruction of what to do during that time. It just had to be a time when the child was not sleeping. So it's a pretty good sample in order to understand what sorts of things children and their caregivers are talking about at home. So this was one of the examples I showed you. Here's another one. And in red, you can see the higher order thinking talk that we coded. So we coded particularly for language that that based on the literature on relational reasoning and reasoning more broadly, we thought would invoke higher order thinking. So here's an example.
What's your favorite part of your body?
If you can hear it.
What do you think? Teeth are your favorite?
Because it's your favorite, because if I didn't have any teeth, then I couldn't eat.
True.
And that's why if I didn't have teeth, then I couldn't eat candy.
Okay.
That's why I would.
Right, logical, you know, you need teeth for candy, most candy. But yeah, so what's here, I think is a really neat because, if then kind of statements, right, from this child. And you notice that the parent has asked this sort of as this, you know, open question, and then the child, and then kind of really sits there and allows the child to come up with her language. And so she's giving this nice sort of causal structure, and she's also using this language. She's using because, she uses if then, and then why, right? So there are a lot of these kinds of tags. Now, there are other times that the language that these kids were producing was higher order thinking talk, but not so meaningful. So here's another one.
Because
Okay, so not as meaningful, right? Basically, why, because. But you see that she's got the structure. She's got the sort of linguistic pattern down in terms of doing this sort of higher order thinking talk. And we think that was actually really important. So, we were interested in looking at the trajectory of the language and sort of how it changed as children accumulated more knowledge, more skill, and more experience with their caregiver. So we coded these, every utterance, reliability, calculated intercoder reliability for all of it, and captured whether this was surface level language, high order thinking language, or more structural. So that why because would be very surface. The structure would be something, richer, right? Like the teeth one is richer. How would I have a temperature? Why do I have a temperature? These kind of structure uses of higher order thinking talk that allowed for more systemic thinking. And we coded whether it was inference, comparison, abstraction, or hierarchy. These are the most common. And when you look at the full data set, you see that inferencing was the most frequent type of higher order thinking talk that was used. And that's not very surprising, but I think it's important in terms of understanding what the landscape of children's inputs looks like. But from now on, I'll collapse them, and I'm going to talk about the surface versus structure higher order thinking talk. And here what you see is that, also not very surprising, the surface talk happens a lot more frequently than the structure, but they both grow over time and with age. So the onset for surface comes first, onset for structure comes a little bit later. But you really do see these reliable patterns in terms of this language production. Now, we also see some other things, like these seem to predict later higher order thinking skill. So early relational talk produced by the child predicted Raven scores later, verbal analogy scores later, as well as two more sort of reasoning, reading comprehension-based measures that are a lot more like a classroom type of learning context. And this was controlling for some key covariates. It was the case that parent higher order talk predicted child higher order thinking talk. So these two were tightly related. We definitely think that the parent's role was important there. However, what's I think very interesting too is that it was the child's talk that predicted their later skills. It was not the parent's talk predicting the later skills. So we'll come back to this theme where it's not just putting children in an environment that has rich higher order thinking opportunities. It's about setting it up to make the child actually do that work. That seems to be what's particularly crucial in terms of supporting this development. All right, and we also looked at a sample. We did the exact same analyses, but with children that had pre or perinatal brain injury, which allowed us to look at income as an environmental characteristic versus brain injury status as neurocognitive factors, and looking at this development trajectory. And just to kind of quickly look at that, we see very similar things in terms of, you can see that the axes are, numbers are bigger on the surface, hot than the structure. So they're more frequently using surface, hot, but you can definitely see this, the importance both of income and typically developing versus brain injured populations. So you see, actually, I don't know if you can tell up there what the difference is, but anyway, the top line is the higher income, typically developing, then you have lower income, typically developing higher income PL and lower income PL. Okay, so it's basically suggesting that income is having a separable effect here from brain injury, and both of them are impacting the nature of the language. So again, not causal, but suggestive that these kinds of language inputs are important and are related to both capacity, but also the socialization and environment. So altogether, we see that children's spontaneous language environment has sort of demonstrates this landscape of everyday relational reasoning use. They are using relational reasoning. There's other experimental evidence already about this, but I think there's pretty clear evidence that young children are using analogical thinking and are using relational reasoning, but they are, and these kinds of early language environments predict where they're going next. Now, how about looking at whether their likelihood of using relational thinking would change on a reasoning task, right? So we looked at ability, we looked at the likelihood of using higher order thinking talk as children, but now I want to think about what this means for reasoning on a particular task in a non-linguistic way necessarily. In this study, we have a bunch of studies. I'd love to talk about this more. I'll just tell you about one that's kind of an experimenter-driven one. This morning I talked about a more parent-driven one, and we can, anyway, have a conversation if anyone would like to. We were interested here in whether we could prime a relational mindset in much the way that we saw that worked in adults. We wanted to know whether you could shift a child to be more relational in their thinking and in their tasks if you gave them a context where they were being very relational. So this was with 4-year-olds, and they were randomly assigned to 2 conditions. Either the child had to generate the relations in between the aspects of the matrix task, or the experimenter generated those relations for the child. And so what we did that as the priming task, and then we did a scene mapping task where we could look at what children were paying attention to in a relational scene. So in this matrix task, in the active version, the child was sort of scaffolded and set up to produce in words they had to actually create, to say the answer to how do caterpillars go with butterflies. So the experimenter had a couple of different prompts to ensure that it was the child who actually generated this, versus the passive one. The experimenter would say, caterpillars grow into butterflies. What grows into flowers? So the child in both cases had to come up with the D term, but they didn't have to do that relational thinking in the passive version. They heard it though, right? They heard exactly the same relations. Then in the mapping task, the way that these work is the top picture, there's a relational scene, and the bottom picture is the same relation, but the features are different. So the top one in this case is a towing scene. So there's a focal object. This one's being towed. We say what is like this in the bottom picture, and there are 2 things. So you could either, you could either pick the relational match, which is also a car being towed, or you could pick an object match, which is a object that looks a lot like the one that was in the top picture. So to cut to the answer, what we found was that the active relational priming group made more relational choices on that scene mapping picture. So despite the fact that young children are theorized to be more objecty in terms of matching than relations, they were pushed to be more relational here, relatively more relational, when they had just done that relation generating task. So it seems like relational mindset can move, it can be shifted, and so it's we think a really interesting place to actually be guiding kids to be attending to relations and sort of more focused on the key relations that we want them to be looking at in the classroom in a learning context. Okay, so now let's think about classrooms. Does this matter? Does it matter that we can get kids to be more relational in their mindsets? If we go back to this classroom idea, we think it's really important because teachers cannot point out everything they want kids to pay attention to. Teachers are experts. They're often not noticing what they aren't highlighting for kids. And so the question is sort of how do we get kids to make those connections? Okay, actually I'm going to skip this, Okay, so how do we get kids to focus on relations? we wanted to look at whether there were individual differences that kids were bringing into the classroom that came based on their relational mindsets. And so our question was, if you have kids who come into a classroom, some of whom are already looking for relations, are they going to learn more than kids who are coming into the classroom not sort of already, not primed in a short-term way, but in a longer-term way in terms of looking for relations? If that matters, then can we teach in a way that gets rid of that difference? Because we want everyone to be noticing relations. We don't want to know that some kids are just going to get more out of the same lesson than another one. So in this study, we did two things. We had two versions of instruction, one of which drew very explicit attention to relations. So it was like lots of higher order thinking talk, look, compare these two solutions. Pay attention to these two right here, right? Lots of attention like that. And the other one was the same instruction, but without those extra cues. We also measured children's relational mindset on a spontaneous scene analogy task. So like the one that I described earlier, it had these two kinds of scenes. And this one, we gave them a bunch more versions, and there's more to this task that I could tell you about. But basically, we gave kids a fair number of these and then created a construct for them and looked at whether they were more likely to be picking making relational matches, more likely to be making object matches, somewhere in between, or totally random. And then we gave the instruction where basically they got a pretest, they got a lesson on proportional reasoning, which is a very relational math context, so it's a really nice one for that. Again, they were randomly assigned to two versions, either this very high order thinking one with lots of attention to relations, or the non-high order thinking version. They got this scene task, and they got an immediate and a delayed post test. We also did an EF test that we controlled for. So when we looked at their scores on the relational attention task, we get 4 latent profile clusters. So that was really the sort of relational attender, the emerging relational attender, object matcher, and then inconsistent responder. We replicated that in another similar sample of children. So these seem to be, somewhat reliable clusters in terms of the types of ways that children are responding to these tasks. And then we looked at relationships to performance. So these are, let's see. You can't see the top of this. Anyway, okay. So this is first to show you what the clusters looked like in terms of responding. Then when we looked at performance at the end, we see that relational attention characteristic did predict learning from the math lesson when prior knowledge and executive function was controlled for. So you can see that here. Basically, the object matchers learned a lot less from that same lesson than those who are attending to relations, which is what we were hypothesizing, and also suggests that, this may create systemic differences in how much kids are learning from a lesson, which gets you to be more relational if you're learning the relational information from the lesson. And if you're an object attender, you're working hard, but you're not getting the relational information. You're just maybe learning the content without being able to be as flexible and transfer, flexibly transfer that information later. Okay, so then we looked at the difference between performance when you put them in the two conditions. So when you looked at learning by condition, you also see this interaction effect. Yeah, so basically, at the delayed post-test, you find that the object matchers benefited more from the instruction that was like the hit you over the head version of extra relational language. The one where we over and over said, pay attention to relations, pay attention to relations. So suggests that that may be a viable way of ensuring that all kids are actually attending to relations. So key takeaways, spontaneous relational attention seems to be a meaningful construct. It seems, at least in this context, to be distinct from maturation, like executive function, and relational knowledge that can also affect learning. But adding these higher order thinking cues to attend to analogy could reduce learning gaps and specifically help children who attended to objects preferentially over relations at the outset to the study. So this could have, I think, important implications in terms of understanding how to ensure that all students are getting the same thing out of a lesson. We know that this is important, but it's challenging, right? How do we get every child to engage in relational thinking, especially if we know that it's not just enough for the teacher to say it, right? It wasn't enough for the parent just to say it or the experimenter. We need the kid to actually generate it. So I'll just leave you with some broad things. We're thinking a lot about AI, right? This is an area where everyone's kind of thinking about it. It's an accelerator. That's how, that's my AI colleagues or my ed tech colleagues think about it. It's like it's able to really accelerate where we're going. If we're, teaching in ways that are kind of not forcing the kid to be doing a lot of thinking, it'll accelerate that too. But if we want to be creative, I think there's real opportunities here to think about how to support something richer. So let's be creative in rethinking instruction, right? I'll tell you, for us, the way that we've been thinking about this is that if we consider our key educational goals and then think about how to use AI to meet those goals, it can just expand your repertoire. So for us, the key thing is to make sure it doesn't do the hard work of thinking, writing, problem solving, that part. We want the kid to be doing that part. So for me, I'm thinking about increasing relational thinking and thinking about how to use Gen AI to scaffold higher order thinking in math. So it's really, can it do this scaffolding work? Meet a child where they are and then give them kind of the bones, but not the meat of that reasoning problem. So for example, here's one task based on a different task I talked about this morning, but Snorkel AI is a lovely interface. It allows for language transcription, and then it'll do the coding on the back end. So it'll say like, oh, it looks like you're doing such and such. And so it'll give these kind of higher order thinking style responses to the kids. So which of these are the most similar? Explain why. Convince your partner why you think so. So this, is a prompt that requires the child to actually do the higher order thinking and sort of state comparisons. We also are working on a chatbot, and it's remarkably easy to create a chatbot, and you can give it all kinds of different cues and supports, and we're working through the training materials. It's not easy to get something to scaffold in a rich way, right? Parents aren't great at it, and it's much harder for a chatbot to do than a parent. But we're working on it, and I think it's really exciting. PlayLab is a really neat place if you're thinking about any of this. So I don't know if you can read this, but yeah, here's one. This is, we're piloting it soon, but looking at the solutions that we had to problems in an instruction module, equivalent fractions versus a double number line. And so we're getting, the chatbot is supposed to not give any answers, but just kind of keep asking questions. Like, it's giving information here. It says, which would you prefer, why? And then, the aim is that the child has to respond, right? They have to be giving these things. So it's fun to play with, and I think I'm hoping inspirational. You can think about how to move forward with these. So with that, I will close and with a video, one more video. I love this one because it is an example of a very unsuccessful analogy, but it is, or a higher thinking moment, but I think demonstrates the hard work that's important when you're trying to get people to actually do this thinking. So I seem to have lost my cursor. I don't know if it's up there. Oh yeah, it is. Okay, so let's see if you can hear this.
Now, what's the ice cream like when you put it in there? Does it look the same?
Mm-hmm.
That's it? Doesn't it look a little bit different?
Mm-hmm.
How's it different than when we put it in there?
Clap, clap, clap.
Was it kind of hard when we put it in there? And what's it look like now? Could we pour it when we put it in there? No, we had to scoop it, didn't we? Now, can we pour it? Yeah. So that's almost like the milk we put in, right? Like the liquid. It's not so solid anymore, is it? Right there.
Okay, so you get the idea, right? So this child is not picking this up, but this parent is persistent. They are trying. They are like, they're talking about state change, right? This is a really rich scientific concept, and they're really trying to get the child to attend to it. And I think that sort of persistence, that sort of work, that kind of scaffolding, that's part of this constructivist way of thinking about supporting kids in building these skills. That's really important, and it's the key. I think that's the key, is sort of how we keep kids focused and doing that relational thinking, even if it doesn't come immediately. Analogical thinking is a powerful part of child development, and language environments, I think, are crucial. Instruction that can harness this attention and cue it for others can accelerate learning and higher order thinking. So maybe Gen AI is one opportunity. Thank you so much. And this work is all collaborative, I should say. So thanks.